So, so let me recall a few things about code. So we know that a code C is simply a subset of fq raised to power n, and then we denote it by C, n, and these are the parameters for query nonlinear code. Right? And if C is a subspace, it's a k-dimensional subspace of fqn. Fu is a field with finite number of elements. Then we denote it by C, n, k, d, q. K is the dimension here, n is the length, and d is the minimum Hamming distance, right? Now let us take the case q is equal to 2. We are looking at the binary case. And so in that case, C is simply a subset of z2 raised to power n. Okay, and we denote it by C, n, m, d. D is the minimum Hamming distance. Okay, and we denote it q by 2. So n is, what is n? N is nothing but the length. Capital M is the cardinality of C, which is nothing but total number of code words, and D is nothing but minimum Hamming distance. So these are the things which you know. Now, I'm again recalling another important fact. There was AQND, okay, which is maximum of all M such that there exist an NMD code. You know, a nonlinear code. So what is the meaning of nonlinear? Nonlinear means whenever we take two code words x and y and sum them, it may not inside the C. It's not closed, need not be closed with respect to addition of two vectors. Okay, so that kind of code is known as nonlinear, right? So in the case of linear, we know that if we take two code words x and y, their sum will be in C itself. You know, so that is our AQND. So it was, you know, for q is equal to 2. So here it is a query code here. So for q is equal to 2, we know that A2 16.6. Now I'm going to tell you a very interesting story actually. It was known that A2 16.6 cannot exceed 2 raised to power 8, which is 256. Right. So that means given length 16 and distance 6, you know, the maximum that you can achieve is 256. So question that was asked, does there exist a code? Question, very interesting question people asked. Does there exist an 16 256 6 binary nonlinear code or not? Does there exist such code or not? This was an interesting question. If it exists, it will be an optimal code, right? Optimal code, because the best possible size and the distance for a given length, you know, you can say that it's the best possible thing. Does there exist such kind of code? So actually, Professor Robinson was giving a lecture about these things in a class, and it turns out that so not some was a student there. He looked at it, this problem, and he said that probably he can construct a binary nonlinear code of this size, And what he did actually, he went home, and after a few days, he actually came back with a solution, and what is known as Nordson-Robinson code. Okay, with the following parameters. He has constructed such kind of code. So it's a very beautiful code. It turns out that, as I told you many times, any beautiful thing can be constructed from some other beautiful thing. And he used Gole code. Gole code is a perfect code, you know. He took the binary Gole code, and by doing some manipulation, he constructed Nordson-Robinson code by doing some manipulation. So I leave it to you to check what kind of manipulation you can do to construct this code. You know, think about it. I'm giving you as an exercise. Okay. How do we construct this code? In fact, today I will give you another way of constructing this code. So, you know, after discovery of this code of Nordson-Robinson code, so basically the code was 16.256.6. I will call it as Nordson-Robinson code. Okay. This code was a binary nonlinear code. Once people find out about this code, they generalize it in two different directions. One direction, they got a code known as Prepeta code with length 2 raised power m, size 2 raised power m minus 2 raised to m 6, known as Prepeta. In another direction, it was generalized. This is a binary nonlinear code to what is known as Caddock code. In Caddock code, parameters are k 2 raised power m, length is 2 raised power m, size is 2 raised power 2m, and distance turns out to be 2 raised power m minus 1 minus 2 raised power m minus 2 divided by 2, where m is greater than or equal to 4 and even. Okay, so in this binary nonlinear code, Nordson-Robinson code was generalized to what is known as Prepeta code, and in other direction it was generalized to what is known as Caddock code. I'm not going to give you the construction. The constructions of these codes are tedious. They used courses of Reed-Muller code, you know. So if you want and if you are interested, of course, you can find papers, relevant papers in literature where these codes are constructed. Now I'm going to tell you something very interesting. You know, what happens? Now you look at the size here. It is 2 raised power m minus 2m, and here the size is 2 raised power 2m. If you multiply them, what are you going to get? So in other words, if we look at, you know, so first of all, note that for m is equal to 4, K4, Caddock code, and Prepeta code is nothing but Nordson-Robinson code. That is one thing. Second thing that you notice, that cardinality of Prepeta code times cardinality of Caddock code is 2 raised power 2m. In other words, full length, you know. Now, as you know that if C is a code, okay, and C perp is a dual code, then they satisfy McWilliams identity, right? So weight distribution of C and weight distribution of C perp satisfies the McWilliams identity. Now, these two codes, Caddock and Prepeta codes, are non-linear. So there is no way that you can assign any algebraic structure here. You know, there is there is no algebraic sense here. You know, they are non-linear. So that means if you take they are not algebraically close. If you take two vectors x and y in Prepeta code, their sum may not be in the Prepeta code, and similarly in the Caddock code. So they are non-linear codes. But they it turns out that they satisfy McWilliams identity. So it was a big enigma. Why? They are not dual. Okay, and you cannot assign dual code here because they are actually non-linear code. So we cannot talk even about, we cannot even talk about dual codes, right? So why they satisfy McWilliams identity? It was a great enigma, great enigma for almost 30 years. It was an enigma for people. Many people tried very hard. They started thinking that probably it's a coincidence, but then there is a beauty here. What happens? Uh, it turns out that they found out that actually you can take Preta code and map it to a code over Z4. Similarly, you can take Caddock code and map to a code over Z4. And it turns out that they were dual to each other. They were related by dual to each other, right? So it means now Z4 is a ring. It is not a field. You saw that in the beginning of the lectures. Z4 has elements 0, 1, 2, 3. And because 2 into 2 is equal to 0, there is a presence of zero divisor. So, so basically, these two codes are dual to each other over Z4. So that means there is a way you can go from Pripeta code to Z4 code and CADA code to Z4 code, and this was actually found by many people first in 1992, then in 1993, and finally there is a famous paper by Roser Hammonds and many others. The paper name is Z4 linearity of Repeta and CADA codes. This paper appeared in 1994. It's a very famous paper, which shows that these codes you can are actually dual when we transform them into. So we are changing the domain here from binary codes. We are converting them into Z4. So how we can do this? I'm going to show you briefly. But before that, we need to, that means, look at codes over the ring Z4. Okay. So codes over Z4. What are codes over Z4? Okay. Z4 is our ring 0, 1, 2, 3. It is known as finite ring. Right? So we look at a space Z4 raised to power n, which is all the vectors of the form x1, x2, xn, such that xi belongs to Z4. And we know that this is not a vector space, rather it is known as, it's a module. In algebra, we call it as a module. Okay. And a code over Z4 is nothing but simply a subset of Z4 raised to power n. Okay. Simply a subset of G4 raised to power n. Subset of G4 raised to power n. And a linear code over Z4 is nothing but a submodule over Z4 raised to power n. Okay, it's a submodule over Z4 raised to power n. And how do we actually So let me actually give you some examples before we proceed further. One very important property, actually one very important thing that will come into picture is, if we take say n is equal to 2, I will show you some examples here. Then we have z4 square. What are the vectors here? 0, 0, 0, 1, 0, 2, 0, 3, right? 1, 0, 1, 1, 1, 2, 1, 3, then 2, 0, 2, 1, 2, 2, 2, 3, 3, 0, 3, 1, 3, 2, 3, 3. This is our module, right? How many? So what is the cardinality of z4 square? N is 2. So of course 4 choices for each coordinate. So we are having 16 vectors, right? Now the question that I am going to ask you, if I want to generate this space z4 square, how we can do that? So one natural way will be, that we take if we take the vectors 0, 1, this one, and say this one. So once you can see that, of course, in the exact sense of linear dependence over fields, in the same way, if we think, of course, we can think that these two vectors are not multiples of each other, right? When lambda is a scalar over z4. Okay, so that means I can generate the whole space z4 square as lambda 1 times 1, 0 plus lambda 2 times 0, 1, such that lambda 1 and lambda 2 belongs to z4, right? So we will get all the 16 vectors when we take lambda 1, lambda 2 in z4, right? I'll take lambda 1 possibilities are 0, 1, 2, 3. Similarly, lambda 2 possibilities are 0, 1, 2, 3. And we get all the 16 vectors. Now, I'm going to take a subcode of it and then see what happens actually. I will take two vectors, and again, just like that, in case of fields, okay. So if I take two vectors and put it in the matrix like this, say 1, 1 and 0, 2. Okay. Suppose this is the generator matrix. That means I am looking at the space spanned by lambda 1 times 1, 1 plus lambda 2 times 0, 2, such that lambda 1 and lambda 2 belongs to Z4. Now what happens? If we try to do the linear combination, you will see that because of the presence of this vector 0, 2, because 0 is a zero divisor and 2 is a, when we take this linear combination, we are going to get repetition. Okay, so if we avoid the repetition, so normally since we are taking two vectors, if we take the linear combination, so we should get 4 choices for lambda 1, 4 choices for lambda 2, so we should get 16 vectors. But this is not the case. Let us see what kind of vectors we are going to get. So I will avoid the duplication here, and you see we will get 0, 0, 1, 1, 2, 2, 3, 3, then 0, 2, then we'll have 1, 3, 2, 0, and 3, 1. 1, 2, 3, 4, 5, 6. Only 8 vectors after the linear combination. Why? Because there are repetitions. When we take the linear combinations, there are repetitions, right? So if I ask you, suppose this is our C, some code C. If I ask you, what is the dimension of C? What will be your question? So what you will do, you first compute cardinality of C, which is 8. There are total 8 vectors. And now this can be written as 4 raised to power 1 into 2 raised to power 1. In other words, this is power 3 by 2, right? So normally you see that is the size of the alphabet that we are taking. Here it is 4. So it looks like the dimension of C is 3 by 2. What is the problem here? So now you see there is a problem here. The dimension is nothing but a fraction quantity. So how to overcome this problem? Okay, so this is a submodule we generated using linear combination of Z4, but it turns out that dimension is a submodule, right? Dimension is a dimension is a fraction 3 by 2, 1.5. So that means something is not wrong. Actually, a nice theory has been developed by some people. In fact, I have also developed some few things here, that what we can do actually, we can define a new way of looking at the basis. So let us see the example. If you look at Z4 square, okay, so there are total 16 vectors. So one way, as I told you, one way, I am putting it in the matrix form, it's a generator matrix, that we can generate all the 16 vectors using this, when lambda1 and lambda2 are over Z4. Another way, very nice way, is if we take matrix of the form 1 0, 2 0, 0 1 and 0 2, and now you take lambda1 and lambda2 scalars to be only on Z2 and not on Z4. So this is known as two basis. You can see that Z4 square now is nothing but lambda 2 plus lambda 2 times 2 0 plus lambda 3 times 0 1 plus lambda 4 times 0 2, such that lambda 1, lambda 2, lambda 3 and lambda 4 to Z2. Okay, so this is a unique way of generating all the 16 vectors basis. Now once we do this kind of thing, so basically what we have done, if there is a vector with one unit, I have multiplied it with 2 and taking that row as a in the generator matrix. Okay, and so for example, in this case of this example here, so this is the standard form. Another way, two bases will be if I take matrix to be 1 1 multiplied by 2 and 0 2. Okay, so here scalars will be lambda 1, lambda 2, lambda 3 over Z2, and it will give you all the 8 elements. So this two basis concept is pretty interesting concept, and this allows us to think that how do we generate these vectors. Okay, and in this case, so cardinality of C is nothing but, so here 8 can be written as 2 cube. So everything we need to do at alphabet 2. So dimension here 2 turns out to be 3. Okay, and is 2 dimension turns out to be 4. Okay, so this is how we can construct the code over Z4, So now basics was very important thing, and we can sort it out like this. Now let me show you general theory now. So basic, in general, generator matrix of any linear, suppose C is a this. Suppose C is a linear code over Z4 raised to power n. This is submodule. So then the generator matrix can be written as ik naught A B1 plus 2B2 0 to ik1 where A, B1, comma B2 and C are binary matrix. Okay, so these are actually, you can put it in the form of blocks also. Because of ik0 and 2 ik1, this portion is lower portion consisting of only rows with zero divisors, full of zero divisors, either 0 or 2. Components are either 0 or 2, right? So in this case, so code C is generated by G. Okay, we can say over Z4, and cardinality of C will be 4 raised to power k0 into 2 raised to power k1. Why this 2? Because there will be repetition, right? Not everything will coming because of the zero divisors. In case of two bases, you can write down the generator matrix. In case of two bases, generator matrix will be ik0 A B1 plus 2B2 and 2 times ik0 2A 2B1 0 2 ik1 and 2C. Okay, this is a and so 2 dimension will be 2k0 plus k1. Okay, 2k0 plus k1. This is the two bases for the generator matrix. Now, so this isn't all about dimension in 2 dimension. Now, what is important here? So this is the standard generator matrix. For code over Z4. Another very important thing is the weight. So we know that normally till now we have studied Hamming weight, right? We have studied Hamming weight with respect to codes over fields. For codes over Z4, we can define another interesting weight known as Lie weight. Lie weight. So how they are defined? Lie weight of 0 is 0. Lie of 1 is 1. Lie weight of 2 is 2. And Lie weight of 3 is 1. So for the units, Lie weight is 1, and for zero divisor 2, it is 2 actually. So if there is a vector x in Z4 raised to power n, one can define vector x as rational sum of Lie weight of the individual components. Okay, and with once we are able to define Lie weight, I can define Lie distance, and Lie distance is between two vectors x comma y over Z4 is Lie weight of x minus y. Okay, So this is how we can define Lie distance. Okay, so I'm going to give you some more examples here. So in general, our linear code C over Z4 can be described by the parameters N, K, DH, and DL. Okay, so K is nothing but 2K0 plus K1 is nothing but 2 dimension of the code. DH is minimum Hamming distance, and DL is nothing but minimum Lie distance. Why do we need Lie distance? It will be clear in a minute. Okay. So also I'll show you an example. If you take code with generator matrix G1 as 1 1 1 3 0 2 0 2 0 0 2 2, okay, this code is equivalent to the generator matrix this 1 1 1 1 2 0 0 2 0 2 0 2. Okay, so you can check that actually. Now the wonderful map which has actually did the transformation of doc and prepara code to a code over Z4 is known as, sorry, gray map. What is gray map? So we are over the ring Z4, and actually we can construct a code over Z2 square by the following map. 0 is mapped into 0 0, 1 is mapped into 0 1, 2 is mapped into 1 1, and 3 is mapped into 1 0. Okay, so this is known as gray map. This map is really very interesting map. Why? Because it is a distance preserving map. It's an isometry. This map, if you call them phi, so phi is a map from Z4 raised to power n. I can extend it from component wise, right? From if I here the map is defined for bit wise, I can extend it to whole vector as well. And Lie distance gives you an isometry. Phi is an isometry to Z2 and Hamming distance. Okay, so that means given a linear code over Z4, if we apply the gray map component wise, I will get a binary code of length twice the code Z4 code, and the minimum Lie distance converts into the minimum Hamming distance. So if I want to construct good codes, good binary codes with respect to Hamming distance, I can look into the Z4 codes and apply the gray map, right? Search for good codes with respect to Lie distance. Once you find a good code with respect to Lie distance over Z4, just apply the gray map and you will get a binary linear code. Sometimes the gray map gives you linear code, sometimes gray map gives you non-linear code. This is an important property. You will see that CADA code and Prepeta code, and actually in particular Knudsen-Robinson code, can be obtained by this map as a non-linear code. Okay, so this is something really interesting thing to do. I will show you by an example here again. Okay. So if we take our code generated by 1102, which we took earlier, so C will be uh, 0 0 1 1 2 2 3 3 and then 0 2, then we have 1 3 2 0 and then 3 1. Okay, these are all 8 vectors. Now after applying map phi, what we are going to get, I will get 0 0 0 0 0 1 0 1 1 1 1 1 1 0 1 0 0 0 1 1, then 0 1 1 0 1 1 0 0 1. Okay, so now you see that here we had a code of length 2, total number of code words 8, right? So I can say that 2 dimension was 3, 2 dimension is 3, and Hamming distance is 1. And what is the minimum lead distance? You can see that lead distance here is 2, here it is 4, and 2 again 2. So lead distance turns out to be 2. Okay, so this is your DL, this is your DH. Okay, and when we map in phi of C, I'm writing in general because unless you are not sure whether you are getting a linear code or non-linear code, we need to check whether we are getting a linear code or non-linear code by looking at these vectors. Okay, so we are getting a code length 4, total number of code 8, so we have capital M, and Hamming distance is 2. Here lead distance becomes a Hamming distance. 2 dimension is 3, so size here will be 8. Here size is also 8, and length is doubling. Here it was n is equal to 2, and here length is 4. So this is how we convert a linear code over Z4 to a binary code. Okay, and the binary code could be linear or it could be non-linear. It all depends. Okay, so now I'll give you some more properties of this code. I can define inner product and talk about dual code. Standard inner product between two vectors can be defined like x1 y1 plus x2 y2 plus dot 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 xn yn mod 4. Okay, if we define inner product like this, I can talk about the dual code is all those vectors x in Z4 is for n such that x dot c is equal to 0 for every c in C. So given a code C, I can define the dual code like this in a pretty straightforward way. A code is said to be self-orthogonal if C is a subset of C per, right? And a code is said to be self-dual if C is equal to C per. And of course, Such kind of codes have been used to do different beautiful things in mathematics. For example, constructing lattices. Okay, and they are also used for some classifications. Interesting thing can be done. Now, one can write down the generator matrix of the dual code as follows: minus b1 plus 2 b2 transpose minus c transpose a transpose c transpose in minus k0 minus k1. Then we have 2a transpose 2 ik1 and 0. Okay, so this is here, and I guess this is like this. Okay, so from the standard generator matrix G, which was given in our notes here, I can show you. Yeah, from this matrix G, we can find out the dual code. So basically from this G, we can find out the dual code, generator matrix for the dual code. You can check that GG transpose is equal to 0 mod 4. So, that is pretty standard thing to do. Okay, so I have given you sufficient machinery to understand what are these codes. Now, some basics of linear code over Z4. Now I am going to give you the beautiful reason why, how we can construct. Now you see, I'm going to give you a brief overview how we can construct Knudsen-Robinson code, which is length 16, total number of code words 256, and minimum having distance 6. How we can construct 16 256 6 code using a linear code over Z4. Okay, as I told you, anything beautiful you want to construct. So we know that in the classical coding theory, there are two beautiful Hamming code, another one is Gole code. So Robinson, in case of Knudsen-Robinson code, they have constructed the code over the Knudsen-Robinson code using Gole code, right? So they constructed Knudsen-Robinson code, which is beautiful, from a beautiful code, Gole code, beautiful Gole code. Now I will show you the construction from Hamming code, which is also beautiful code, right? So let us see how we can do that. So in order to do this, what we do, take the generator polynomial gx as x cube plus x plus 1, which divides x raised to the power 7 minus 1. This is the generator polynomial for the Hamming code, right? So what we do, we uplift it. It is known as Hensel uplift. Capital G of x, which is a polynomial x cube plus 3x square plus 2x plus 3, which divides x raised to the power 7 minus 1 over Z4. This is over Z2. There is a difference. So we started with a binary cyclic code, so a code generated by a polynomial x cube plus x plus 1, which is factor of x raised to the power 7 minus 1, right, over Z2. We Hensel uplift to a polynomial gx such that when we reduce gx mod 2, I should get a small gx. Okay, when we reduce capital Gx mod 2, we'll get gx. Hensel uplifting is a way to uplift a polynomial from binary to Z4. Now we actually construct a code using this polynomial over Z4, and so this can be done like I write down the coefficients. Okay, 0, 1, 2, 3, 4, 5, 6. Okay, and then I'll be adding a page check symbol. 3, 2, 3, 1, 0, 0, 0. 3 is the leading coefficient, then 2, coefficient of x square, and coefficient of x cube. Then, okay, I 3, 2, 3, 1, 0, 0. Again shift it 0, 3, 2, 3, 1, 0. Okay, and again shift it, you will get 0. Sorry, you will get 0, 0, 0, 3, 2, 3, and I'll add a petty check symbol modulo 4. So this is our generator matrix of a code over Z4, and this code is known as Octa code. Okay, so from the generator matrix we got the Octa code. If we take the linear code of this linear combination of this code, actually we will get 8, so this is length, this is 2 dimension. Okay, because of the structure of the vectors, they're all linearly independent actually, in the normal sense. And then we take the 2 linear combinations. So basically, I can multiply, because there is a unit in each row, I can multiply each row with with 2. So there will be total 8 vectors in the generator matrix. So this code is nothing but the Octa code. You can see that the minimum lead distance turns out to be 6. Okay, so cardinality of 08 is 4 raised to power 4, or in other words 2 raised to power 8, which is 256. When we apply phi gray map on this Octa code, we get length 16, 256, 6, Nonson-Robinson code. Beautiful. It's beautiful construction, right? What is the Nonson-Robinson code? One can this code is also served you over there are some other generator matrix as well, which I can just mention here for you. G is 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1 3 1 2 1 1 2 3 1 3 3 3 2 2 3 1 1. Right, this is our the construction. So I think I have explained to you how to get this Nonson-Robinson code, a binary nonlinear code, from a linear code over Z4, right? So this construction can be extended in different directions. There are characterizations. So given a code, binary code, whether it is linear or nonlinear, when it can be represented by a code over Z4, there are characterizations. Okay, there are properties when we can check those properties. It turns out that Reed-Muller code are not representable over code over Z4. Okay, certain codes are representable over Z4, and especially this CADA code, Prepeta code, you can construct them from a linear code over Z4. Okay, that's a beautiful construction. There's a lot of literature since 1994 and on this topic about linear codes over Z4. So I think that's all for today. In the next class, we are going to start finite fields in more details so that we can give you in future the construction of BCH code, and then as a special case Reed-Solomon code, and finally we will come to the convolutional codes, and then we'll talk about a couple of applications so that the basic coding theory is done.